Well, the first thing we do, of course, is that we want to align our Gibbs free energy surface. In this case, we're calculating the Gibbs free energy formation of N2O4 under standard conditions on the ordinate of the left-hand side, the reactant side, and we want to also plot the Gibbs free energy of formation under standard conditions for the product, in this case NO2. Well, we've just done that, and remarkably we've now calculated the change in Gibbs free energy for the reaction. That's plus 5.3 kilojoules. That means that if I run a line along the Gibbs free energy associated with the reactants, and I run a line along the Gibbs free energy for the products, it means that I have gone up by plus 5.3 kilojoules in going from N2O4 to NO2. Well, I immediately know something, and that is that that's uphill thermodynamically. I also know that if I were to start with pure NO2 instead of N2O4, the Gibbs free energy surface would slope downward because I know I have to drive back to the equilibrium position. Equally true, if I start with pure N2O4, then I'm going to move from left to right because delta G is less than 0, and I know delta G must be less than 0 in both cases because that's the only way I can achieve equilibrium, because I know equilibrium is going to sit out somewhere between pure reactants and pure products. And that equilibrium position represents the lowest point on the Gibbs free energy surface connecting reactants and products. And so I can now complete my diagram, because for NO2 on the left and N2O4 on the right, I have moved down the free energy surface toward the equilibrium point from pure reactants, just as I have moved down the free energy surface from pure products until I find the magic point where delta G is equal to 0, and at that point I'm in equilibrium. Namely, the rate of the forward reaction converting N2O4 to NO2 exactly matches the reverse reaction of NO2 forming N2O4, but those reactions are going on at a furious rate constantly, but that very delicate balance is established by the fact that the system has to drive back to the equilibrium position. Now we have established the character of the free energy surface and how important it is for establishing equilibrium. But we also want to link that calculation of Gibbs free energy of formation for reactants and Gibbs free energy of formation under standard conditions for products back to our representation of the relationship between the equilibrium constant and the reaction quotient. And recall the fact that we can write the equilibrium in concentration terms, which we label K sub C, and that's equal then to NO2, the quantity squared, divided by the concentration of N2O4 at equilibrium. But we also recognize that we can write the reaction quotient, Q, in exactly the same form, not at equilibrium. And so were we to apply a stress to this system, we could write down Q immediately, knowing the concentration, but we also know that the system is going to drive such that Q moves back toward the equilibrium constant, the value for the equilibrium constant. So if we were to start with a Q larger than the equilibrium constant, we would shift from right to left, coming back to the equilibrium point. If after the stress we have a Q that's less than the equilibrium constant, then the system shifts from left to right until it finds that magic point representing delta G equals 0.